While that was happening in Chile and Hawaii, another witness waited in the most precise labs on Earth. If alpha drifts, even by a hair, time itself, measured by our best clocks, should start to disagree. If laws are weather, clocks become storm gauges. Field hint lab verdict. We leave starlight and ask clocks if the rules are moving now. Atomic clocks start talking, timekeeping versus time itself. Time isn't what you think. Atomic time is a peace treaty, not a law. Screenshot this. If the laws drift, atomic time is just a consensus fiction that needs a weekly patch. If alpha drifts, the universe won't announce it with fireworks. Our best clocks will just start to disagree. That's the stake, timekeeping versus time itself. Navigation satellites, finance timestamps, power grid phasing, everything assumes the ticks are identical everywhere. If the constants move, the ticks won't line up, and the world we've built on synchronized pulses starts to slip. Nobody tells you this when they sell atomic time. It's only as absolute as the constants behind it. Action starts in quiet rooms filled with lasers. Optical lattice clocks trap thousands of atoms, strontium, ytterbium, floating in a standing wave of light tuned to a magic frequency where two atomic states shift together. That trick neutralizes one of the nastier systematics and lets you stare at a narrow transition that barely blinks under perturbation. Meanwhile, single-ion clocks, aluminum, ytterbium ions, bet on one perfect atom, shielded, interrogated, counted. Different species respond differently to alpha. That's the whole point. Teams compare frequency ratios, not just absolute frequencies, because ratios cancel noise. If alpha changes, those ratios drift with telltale slopes. This isn't one experiment, it's a global relay race. NIST tightens one link, NPL another, PTB and RIKEN polish the rest. Fiber links snake between labs. Frequency combs slice optical light into countable teeth, bridging colors to microwaves to compare everything with everything. Year after year, the plots extend. The slopes, usually indistinguishable from zero with uncertainty bars shrinking like a vise. Constraints tight, parts in 1017 then approaching 1018 per year with state-of-the-art optical clocks now bounding drift at roughly 1018 per year locally. But every so often, a trend flirts with significance. A tiny slope over a few years, a wobble that tracks Earth's orbit around the Sun, hinting at a coupling to gravitational potential, not time. Then the next data release flattens it. Systematic, maybe, temptation, always. Complication lives in the margins. Temperature shifts in the lab floor feed into blackbody radiation shifts. Laser intensity breathes, changing AC stark shifts. Collisions between atoms in the lattice nudge the transition. Magnetic fields creep. The teams fight each gremlin with metrology jiu-jitsu. Cryogenic environments to quiet blackbody noise. Quantum logic readout for ions that don't fluoresce. Interleaved operating points to subtract biases. Remote comparisons over stabilized fiber to avoid transporting clocks physically. They don't just run one clock, they orchestrate a network. QSNET and similar consortia set a goal, cross-compare dissimilar clocks for years. Strontium versus ytterbium lattice, aluminum versus ytterbium ion. Add in molecular systems, calcium monofluoride molecular ions, whose vibrational lines lean hard on the proton-electron mass ratio mu. If alpha drifts, one set of ratios moves. If mu drifts, a different pattern moves. Overlapping sensitivities turn the network into a fingerprint scanner for physics. Here's a human moment. A grad student watches an overnight run, every data point a tiny dot marching across a screen. The lab hums, the air smells faintly of warm electronics. 2 a.m. coffee cold, a text from a collaborator on the other side of the world. Check the room temp log. The HVAC hiccuped by half a degree at midnight. The slope you thought you saw dissolves when you correct for it. Relief and disappointment land together, hands on temples, a long exhale. Back to zero, back to truth. And in the group Slack, a pinned message, no press, not yet. Impact arrives in two directions. First, the limits themselves reshape theory. If alpha is dancing, it's doing a slow waltz, not a sprint. constrained to change less than a part in 1018 per year locally. That squeezes models where a rolling scalar field pulls constants along. If a field drives the quasar dipole, it either barely touches Earth today, or it couples in ways that hide from these clocks. Second, the very act of pushing precision remakes timekeeping. Optical clocks now outrun the old cesium definition of the second. The metrology world is preparing to redefine time on optical standards, locking civilization tighter to the quantum bones of matter. But there's a subtle twist the lab folks lean into: gravitational redshift. Move an optical clock up or down a few centimeters and you can measure Earth's gravity. That's not a side project. It's a new tool called chronometric geodesy. Build a continental mesh of optical clocks and you map gravitational potential in real time. The same mesh, watched for years, becomes a drift detector. If a cosmological field is whispering through physics, a spatial pattern should imprint on the network. That turns the planet into a physics sensor, and your city into a pixel on a live map of reality's drift. Meanwhile, speculative hints keep popping up. A few studies report annual modulations in ratios, matching Earth's distance from the Sun. Others put strict upper limits on any coupling between fundamental constants and gravitational potential. The battle is in the decimals. Every time a group claims a wobble, 3 others try to crush it with better control, longer runs, different atoms. Today's best limits push drift down to roughly 1018 per year, and null out most proposed seasonal couplings. What nobody knew 5 years ago and people are quietly betting on now is whether clocks will make the first definitive catch. There's a nuclear clock on the horizon using thorium-229's ultra-low energy nuclear transition. If that transition is as sensitive to alpha and the strong force as predicted, it could be the new champion, less noisy, more responsive to the physics in question. If constants drift, a thorium clock might see it first. Thumbnail line: the second is about to change. Stakes again. If these clocks stay flat for another decade, many varying constant models will be on life support. If a cross-checked, multi-species network sees a coherent drift, everything from quasar data to quintessence gets a hard shove. Either way, the lab has become a courtroom where the universe testifies under oath. While that quiet trial continues, the Earth already ran a long experiment for us. 2 billion years without a lab notebook, but with results etched in ore. The natural reactor that shouldn't exist, Oklo's fossil physics experiment. The Earth left us a warning. A reactor ran for 300,000 years without us and kept the receipt. The Earth left us a lab note in stone. 2 billion years ago in what's now Gabon, a uranium deposit did something nobody expected. It went critical on its own. No control rods, no concrete dome, just groundwater trickling through rich veins of ore, moderating neutrons until fission lit. It pulsed for hundreds of thousands of years, heating, boiling off water, pausing, then starting again like a breathing geologic heart. When it finally died, it sealed a message in isotopes, a record of physics as it was back then. Here, that's why that matters to alpha, to constants, to our whole argument. Fission isn't just heat, it's a ledger. Each neutron capture and decay leaves behind ratios: samarium, neodymium, ruthenium, xenon, shaped by nuclear cross-sections. One of those is especially sensitive to the fine structure constant, samarium-149. Its ability to eat neutrons spikes near a resonance whose energy depends on the strength of electromagnetism threaded through the nucleus. Shift alpha a hair, and that resonance slides, changing how many neutrons samarium-149 grabs, and therefore how much samarium-149 survives in the rock. In the early 1970s, French chemists noticed that the natural uranium shipped from Gabon had less uranium-235 than expected. That's the fissile stuff. It looked like someone had already used it. The investigation led to Oklo and then to a forensic read of the reactor zones. 72 tons of uranium-235 gone, traces of fission products right where they should be. It wasn't a fraud. It was a fossil reactor. Now take that fossil and turn it into a test. Measure the samarium isotopes. Reconstruct the neutron spectrum that must have existed to fit those ratios. Ask what resonance energy for samarium-149 would produce that spectrum. Then translate that energy into a bound on alpha at the time. Do the same with other isotope pairs to cross-check. Neodymiums tell, xenons trapped gases in ancient minerals. Each one points, indirectly but consistently, to the nuclear environment and the constants that set it. Nobody told the rock to lie for us. It still says little or no drift here. The headline result, repeated with refinements for decades. If alpha changed at all since Oklo ran, it didn't change by much. The bounds land at parts per 10^8 over 2 billion years. In plain terms, less than a few parts per 100 million. That's a wall for any theory that wants alpha to be wandering fast. Oklo says, not here, not by much, not in the deep past of this planet. But here's the twist scientists argue about in hotel lobbies at conferences. Interpreting Oklo isn't plug-and-play. The neutron spectrum depended on the reactor's geometry, the water content, the temperature cycling, and the composition of the surrounding rock. The resonance energy in samarium-149 doesn't depend only on alpha. It leans on the strong force too, on nuclear structure encoded in models that carry their own uncertainties. The translation from "we measured samarium" to alpha was X plus or minus Y passes through a forest of nuclear theory. So the debate lives in the error bars. Update the nuclear models, rerun the Monte Carlo simulations of how the reactor breathed, and you can nudge the inferred resonance by a few tens of millielectron volts. That's enough to shift the bound on alpha's change by a factor of a few. It doesn't open the floodgates. It does keep the door cracked for slow drifts and for compensating changes, alpha moving one way, a strong interaction parameter sliding the other, leaving the resonance almost put. Human angle. Imagine being the person who spends 3 years coaxing xenon atoms out of ancient mineral inclusions, molecule by molecule, to count isotopes from a reactor that shut off before complex life walked. Or the geologist who maps the reactor zones, hands black with laterite, trying to reconstruct where the water flowed. Or the nuclear theorist who stares at a line in a calculation and realizes a correction term everyone ignored in 1985 might matter at the exact sensitivity Oklo demands. Every small fix warps the story slightly. The humility is baked in. This is a time capsule, but not a perfect one. There's also a broader meaning that makes Oklo more than a bound. It shows that under the right conditions, nature builds a reactor that holds onto its waste for geological ages. The fission products barely moved. If the constants had drifted substantially, many of those products wouldn't line up with the retention we see. That stability hints at something else. The Earth's conditions and the constants that shape them were steady enough for this slow machine to run and then sit undisturbed for 2 billion years. Meanwhile, the skeptic's case stands. If you want to claim that quasar spectra see a spatial dipole in alpha at the parts per million level, you have to reconcile that with Oklo's time-average stability at parts per 10^8 on Earth's world line. It's not impossible. A dipole can be spatial, strong far away, weak here. A field can roll in the early universe, then freeze by the time Oklo runs. Or different constants can co-vary to keep sensitive nuclear resonances pinned even as alpha alone would push them. Gatekeepers lean on Oklo like a shield. Come back when your anomaly passes this rock. Screenshot this. You don't beat a 2 billion year reactor with a glitch. You beat it with a theory that survives it. If your model can't pass Oklo clocks in the sky at once, it's not a model, it's a story. What nobody knew when Oklo was first dissected is how central it would become to the culture of this debate. It's the anchor slide in talks, the quiet benchmark that forces theorists to fine-tune their knobs. And it's a reminder that our planet has been measuring for us the whole time, leaving clues in ore and clay while we learn to count them. Deep time narrows the window. Deep space still teases it. So we turn to the early universe's own photograph, the cosmic microwave background, to see what was imprinted when everything was hot, dense, and young. Cosmic microwave background and the early universe's signature. The baby picture with a secret. While deep time wrote clues into rock, the early universe wrote them into light. The cosmic microwave background is the baby picture. Photons launched when the universe cooled enough for protons and electrons to hold onto each other. That last scattering moment froze ripples into a mottled pattern across the sky. Hidden in those ripples is a ledger of the constants that set the rules back then. Here's the stake. Change the fine structure constant in that hot plasma and you move everything. How tightly atoms bind, how often photons scatter, the exact timing when the fog clears. Those details shape the angular power spectrum, the peaks and troughs that Planck and WMAP mapped with ridiculous precision. Shift alpha and the peaks shift with it. Screenshot this. The baby picture has metadata. Touch alpha, the CMB edits itself. Action first. Satellites spent years scanning the whole sky, stripping out foregrounds, calibrating detectors, and collapsing a billion temperature measurements into a spectrum. The first acoustic peak tells you the size of the sound horizon, how far pressure waves traveled before recombination. The second and third peaks tell you the ratio of baryons to photons, the amount of dark matter, the damping at small scales where diffusion erases contrast. All of this is sensitive to how easily electrons and protons meet and stay together, which depends on alpha. Make alpha larger and hydrogen binds more tightly. Recombination happens a bit earlier. Photons decouple sooner. The sound horizon is smaller. The peak positions slide. Planck teams fit models to this spectrum, not by eye, by exploring a high-dimensional parameter space. The standard set includes 6 core parameters. Add a knob for alpha, let it float, and ask the data how much wiggle room is left. The answer is, not much. If you keep the rest of the model intact, flat geometry, cold dark matter, a cosmological constant, the CMB locks alpha near the present value within a few parts per thousand at recombination, and fixes H0 near 67 km/s/MPC in that framework. That's a broad brush compared to the quasar ppm whispers, but it's at a time 380,000 years after the Big Bang, when the physics was very different. The early universe says, you can't move alpha far without messing up the peaks. But there's a catch, the degeneracies. Vary alpha and you don't just move one dial's output. You can partly compensate by adjusting the baryon density, the Hubble parameter, or the scalar spectral tilt. That's the model dependence trap. If alpha creeps, the fit can shove other parameters to soak up the change. The spectrum still looks good, but your measurement of alpha now depends on choices under the hood. Planck papers spell this out. Constraints tighten or loosen depending on what else you allow to float. Meanwhile, polarization adds a second witness. The E-mode polarization peaks arise from the same acoustic physics but respond differently to scattering. Fold in polarization, and the parameter covariances shrink. You get sharper bounds on recombination history, hence on alpha then. The fits still say small wiggle room, percent level at most, but the path there shows how interlocked the constants and cosmological parameters are. Here's where the human debate gets loud. One side, the CMB kills large variation, end of story. The other, careful. You've assumed a cosmological constant, fixed neutrino physics, and no exotic couplings. Relax those and alpha's leash lengthens. Papers trade scenarios. Allow early dark energy, allow extra relativistic species, allow a time-dependent dark energy equation of state. Each one stretches or tightens alpha's corridor. While that's happening, a deeper point bubbles up. The CMB is mostly sensitive to dimensionless combinations, ratios that don't care about units. That's a sanity check. Change a dimensionful constant like c by definition and you're just changing your ruler. What matters are the pure numbers. Alpha, the electron-to-proton mass ratio, the gravitational strength in Planck units. The CMB, like the quasar spectra, cares about those. Impact. Even with degeneracies, the early universe sets guardrails. No model where alpha wandered wildly through recombination survives without breaking the peak structure.